Queria agradecer a presença de todos vocês, tá certo? Dizer que hoje à tarde a gente tem uma nova palestra denominada Métodos de Pesquisa Misto e Revisão de Pesquisa Mista, uma janela de oportunidade científica, da professora Maria Cristiane Barbosa Galvão, da Faculdade de Medicina, no dia 17 de maio. A origem e a evolução dos buracos negros, João Evangelista Steiner, do Instituto de Astronomia, Geofísica e Ciência Atmosférica da USP. Queria chamar o professor Antônio José Costa Filho, tá certo, que vai apresentar o professor Alan Dalton, da Universidade de Serve.
Bom dia a todos. I'm going to switch to English now so that you know that I'm not saying anything bad about you, Alan. So it's our great pleasure to welcome here today Professor Alan Dalton from the University of Surrey. So Alan is here in Ribeirão Preto, along with two other colleagues, Professor Alex Smirnov, who is in the back there from North Carolina State University, Professor Tatiana Smirnova, also from North Carolina State University. So they are part of a trilateral collaboration project between USP, University of Surrey, and North Carolina State University. So they've been here for like 3 days, very intense days, and we invite them to give talks. Alex and Tatiana gave talks at our department last Wednesday. And today we finish up our activities in the project with Alan's talk. So Alan has received his PhD from the Trinity College in Dublin, right? Mm-hmm. And he was a fellow in Dublin still, and then went to the US for a postdoc. And now he's a professor at the University of Surrey. He's going to talk about his recent work on nanostructural materials, which is, I believe, is a topic of very broad relevance for many of you in the audience. So I want to publicly thank you, Alan, for being here. Thank you, Alex. Thank you, Tatiana. So you are all very busy persons, I know that. So thank you for coming at such a rush, and I hope you've enjoyed. So, Alan.
Thank you, Antonio. So it's a great pleasure to be here. So what I thought I'd do is give you a broad overview of some of the work that we're doing, my group is doing in this area. And it's really about using nanostructured materials, meaning building materials at the nanoscale, and translating those properties to the macroscale for applications, so for functional materials. So I'm from, as Antonio said, I'm from the University of Surrey in the UK, and this is our campus. It's much smaller than your beautiful campus here, but it's pretty enough. We've got a lot of greenery. So I'm in the Materials Institute, which is over here in the Department of Physics. And so Surrey is down here in this pink box. We're about 30 kilometers or so from the centre of London, so it's a half an hour on the train. And it's a very pretty place to visit if you ever get a chance to go to the UK. Okay, so what I'm going to talk to you today about is methodologies to make nanostructured materials with enhanced performance, enhanced properties. And the subtopic of this is learning from nature. Okay, so many of the materials that one finds in nature that have specific functionality. That could be mechanical strength. It could be electrochemical activity inside the body. It comes about because nature has managed to build materials in a very controlled way from the nanoscale to make microscopic and macroscopic materials. And I know that in your particular campus, it's heavily biology oriented. And this particular area of science requires that physicists and chemists, to a lesser extent, and biologists talk together. And I think it's only since in the last 10 or 15 years that we're beginning to speak the same language. So we're talking about the same things, but we're talking in very long equations, and you're using very long words. So up until now, it's been a bit of a problem, but we're beginning to get there. And I think the interaction or the marriage of these different areas has been very fruitful in terms of our understanding of natural materials and then translating that understanding into making synthetic materials with excellent properties. And If we look at some very beautiful examples from nature, where nature has built, or Mother Nature has, over many millions of years, developed materials with specific properties to do specific things. And there's a few examples I'd like to give you. So one is the gecko, and specifically gecko feet. So gecko feet, if one looks at the microscopic level, have these pod-like structures, but on the end of the pods, you have very fine nanostructured fibrils. And they use these, and specifically the van der Waals forces, so the electronic interactions on the nanoscale, to climb very flat surfaces. And this is a very nice image of that, where you have a Teflon surface, so extraordinarily flat surface, and this gecko is using these pods, and specifically the nanoscale brushes on the pods, to walk up and down this particular wall. And it's completely flat. There's no corrugation. So it's utilizing so-called van der Waals forces, which have been predefined by the nanoscale structure of the pod. Another beautiful example is the lotus leaf, which has self-cleaning properties. And it has self-cleaning properties because of the nanoscale structure on the leaf. So if one looks on the microscopic and nanoscales of this particular lotus leaf, we can see that you have a combination of nanoscale corrugations and also differences in the chemistry along the local structure. And what that means is you produce a very hydrophobic or water-hating surface. So if one compares the lotus leaf to a smooth surface, so for a smooth surface, a water droplet comes down and it spreads over a large area. Okay, so there's not enough capillary interactions to take dirt off the surface, and therefore the water bead flows down and it leaves dirt or other materials on the surface. For the lotus leaf, you have this nanoscale corrugation and also differences in the chemistry, which produces a hydrophobic effect, and therefore the wetting of the water droplet changes, and it can actually take the dirt and clean the leaf surface. So how do we learn from nature to build synthetic materials with the same functionality as we see in many natural systems? Okay. So if we look at the differences so if I want to build a material, I'm an engineer, I take bricks, I take cement, I put one down, I put cement down, I put another brick, and so on. In nature, everything done is in liquid, and it uses specific low-energy interactions to assemble materials. So those materials are based on amino acids that form peptides, that form proteins, and act as tertiary building blocks to make specific functionality. So this is a beautiful example, a macroscale example, where we have polymer shapes of triangles, but on the edges of the triangles, they've been coated with a ferromagnetic material. So you just mix it all up in water, and eventually the magnetic force, coupled to the triangular shape, will get all of these specific shapes to assemble into one material. Okay? Now, on the macro scale, so these are microscopic particles, we're using magnetic energy, but the same principles apply on the nanoscale in biology. Except in biology, on the nanoscale, it's thermodynamically driven. Okay? So it's weak van der Waals forces that are bringing these individual nanoparticles together to form functional materials. And that's based on two principles. So the first is that these interactions tend to be shape-specific. So in this cartoon, I can't put a square peg into a round hole. And also thermodynamically driven. So in biological systems, these materials or these building blocks form to lower the energy of the system. Okay? Or to lower, in physics terms, reduce its free energy. And the real key thing is this is all done in an aqueous environment, so these things will come together via Brownian motion. And if all of the influences are correct, we begin to form macroscopic complexes of these nanoscale building blocks, but in an ordered way. Okay, so how does this work? Well, we start with amino acids. They form oligomers and then polymers. We have these peptide chains that then fold into secondary structures like helices or sheets. They form tertiary structures, which eventually can be coupled into very macroscopic systems like cells. And of course, ultimately, the ultimate nanotechnology machine is us as people. And of course, I believe, so I was talking to Antonio last night, and I'm a big soccer fan. And normally I put an Irish footballer up in this picture. But I thought that because I was in Brazil, Socrates is from here, I think. So, and for me, he was one of the geniuses, one of the greatest footballers that ever existed. So if we have ultimate perfection in our assembly, Socrates could be it. And he also liked a beer. So I like a beer as well. So. Okay, so if we can take the natural assembly principles and apply it to synthetic materials, then perhaps we get the best of both worlds. We can use the physical properties of synthetic materials, but in structural assemblies based on biological principles. And perhaps we end up with materials with physical properties and chemical properties far outreaching what's available to us at the moment. And there's a plethora of synthetic materials available. I've just shown you 4 here because my group work generally on these materials. So you may have heard of graphene. I'll say something today about graphene, but graphene is essentially a single layer sheet from graphite, so this is the pencil graphite. And 2 professors from Manchester won the Nobel Prize for the discovery of graphene, or the processing of graphene, a few years back. We work a lot on carbon nanotubes. There's also a lot of very nice work on metal nanowires and on polymeric nanospheres, and I'll say something about that at the end of my talk. But the key is that we're now using building blocks that are on the level of atoms, so atomically thick material. And if we can control the material properties on the nanoscale, well, we can utilize the fundamental interactions, the strength of bonds, the friction of nanoscale. Everything changes when we go to the nanoscale in terms of the physics and the chemistry. So if we can utilize that and control it, we could perhaps make macroscopic materials with better properties. Okay, so I'll give you a little bit of detail about some of the work we've done on carbon nanotubes. So carbon nanotubes are a very beautiful material. You take a sheet of graphene and you roll it up into a cylinder, a seamless cylinder. And the properties of the nanotube are dependent on how one rolls the sheet, so the angle we roll it at, which is called based on the chirality, and also on the diameter of the sheet, okay, or the tube. And if one can control that, one can control both the electric properties, the thermal properties, and the mechanical properties. So it has very amazing physical properties, so thermal conductivity better than copper, very high surface area, so one can use it in batteries, supercapacitors. It has extraordinarily high tensile strength and Young's modulus, which means stiffness. And that's because the material is breaking on the nanoscale, and that breaks by chemical bonds breaking, and they're very, very strong. So one can see this type of material as being the ultimate and the best, right? So the James Bond of materials. And of course, because Sean Connery is the best Bond, carbon nanotubes are, of course, James Bond. So, but there are problems, and there are many problems. And the problem is that when it's produced, the carbon nanotubes are in the form of an extraneous soot, right? So very low density material that's very hard to process. So we have to look at this, and if we look at the nanoscale, so it's almost like a spaghetti entanglement. And if we go even further, these individual nanotubes form rope structures. So we need to disassemble the nanotubes into a processable form and then re-aggregate them into a controlled structure. So we do that by going to solution. So we make some kind of dispersion of these things, and then we try and control the reformation into materials. And we can form fibers or sheets or composite structures with polymers and so on. But this is a big issue, right? So the problem is that when we make macroscopic materials, often the properties are far less in terms of mechanics, electrical, and so on, compared to the nanoscale components themselves. So if I qualify it then, it's maybe not Sean Connery. It's probably the new Bond, so Daniel Craig. It has a lot of potential, but it's not quite there yet. All right, so let's go back to learning from nature. So I'm an alien, and I'm on Mars, and I'm looking down at Earth, right? And so what do I see? I see lots of machines. So I see lots of cool cars, so taxis in New York and so on, police cars in Boston, trucks, whatever I say. And I say, well, these machines are pretty good. They get people around, but they're not great. What if I could take them apart, I could disassemble them, and bring them back together in an optimized fashion to make, for instance, Ferraris or Harley-Davidsons or Formula One cars, right? So the idea is we have a database that this alien sees, and he deconstructs these cars into their constituent parts, so steering wheels, belts, pumps, whatever, and he reassembles them into something cooler, right? And so this is what we want to learn from nature, right? So nature makes incredibly complicated structures with specific functionality, but on the very base level, that's made of very, very fundamental basic building blocks. So these are peptides that form helices or sheets. And what if we could take those basic building blocks and use those building blocks to assemble our synthetic materials into cool structures, right? So we're essentially using biological templating to assemble our nanomaterials into macroscopic assemblies. So we could take these peptides and we could use them to now assemble macroscopic structures, but now we can integrate our carbon nanotubes or other nanomaterials. And we've done this, and so we've worked on this for several years now, where we use synthetic de novo peptides with specific, very simple design, and they act very well as dispersants for carbon nanotubes. So carbon nanotubes are a very hydrophobic or water-hating surface. Once these peptides fold, one side of the peptide will have a hydrophobic face, and one side will be hydrophilic, so it'll like water. So essentially, it's a biological surfactant, detergent. So we can use this to disperse the carbon nanotubes. And this is a transmission electron micrograph. So this is one carbon nanotube, so 1 nanometer across, so roughly 10 atoms. And the peptide is wrapping itself around the nanotube periodically. And this is just a computer image of that. And on the right here, just to prove this is what we have, this is a scanning tunneling micrograph. So we're using quantum tunneling of electrons to image the nanoscale structure. And this, again, this is 2.5 nanometers across. So we have our carbon nanotube, and this is the peptide wrapping around. And if we look in 3 dimensions, it's easier to see. So now we have a defined nanoscale building block that couples perhaps biological assembly with the synthetic nanostructure. And we can then think about using this particular hybrid to assemble the nanotubes into controlled structure. So in this cartoon, that's what we want to do. But in fact, it works very well. So in the same way as natural peptides and proteins come together in an ordered fashion, we can force our peptide nanotube assemblies to do the same thing. So one way of doing it is to change the chemical environment around the nanotubes. And in that respect, we use salt to quench the charges or the polar groups on the peptide. So we go from this dispersion to a controlled aggregation. We can form fibers, so these fibers are 50 microns across, so many millions of nanotubes. Or we can thermodynamically drive this, so we can change the temperature, and one can go from an isotropic system to a highly aligned system. And we're just using simple physical probes or changes to force the peptides to assemble and bring the carbon nanotubes along into the assembly. You can be clever about this, and you can think about new types of devices. And one thing one could think about is, what if we could use carbon nanotubes to act as sensors, gas sensors, but do it on the molecular level? So have a sensor based on one carbon nanotube, and then as a material from outside absorbs on, we measure changes in electrical properties, or we measure changes in mechanical properties of the carbon nanotube. So this is, again, a scanning tunneling micrograph, and you can actually see the individual carbon atoms in a free area, right? So this is the hexagonal array of the carbon atoms in the carbon nanotube. And we coat certain regions with peptide. And if we then look at the electrical properties, so we don't have to go into this in too much detail, but essentially what we're doing is we're taking current voltage curve, so typical electrical properties, at each nanoscale point on the carbon nanotube, right? So we end up with some kind of current versus voltage, as one would get in an engineering lab, but it's on every single point, on every atom along this particular system. And then from that, we can look at what's called the density of states. I don't want to go into the physics of this. I'm not sure, how many physicists have we got? One. How many half physicists have we got? Okay. So there's a way, if we look at the change in current with voltage, and we plot that as we change the voltage, essentially what that plots is the density of states versus energy. And what the density of states is the probability to find an electron at a particular energy. So if there's a high probability, then you have very high peaks in your density of states. And because the carbon nanotubes are one-dimensional, so those states are quantized and they can only take particular energy levels. So if this was a normal semiconductor, it would go boom, 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 boom. Okay? If it's graphene, it would go boom, boom. Because this is one-dimensional, we get lots of spikes. Okay? So there are only specific energies that the electrons can take. And if we look at the uncoded region, so we have some kind of shape here where each one of these is a state that the electrons can take. And when we code it with the peptide, there's electronic interaction, and therefore the density of states changes. And in fact, what we're doing is we're putting a state in the band gap, which is essentially, in physics terms, we're tuning the Fermi level. So this is a direct way of looking at single molecule absorption on a nanotube. So we're making sensors on the nanoscale. I won't go into this today, but one of the other things one can do with this is we can use the peptides and control the peptide chemistry to controllably insert the carbon nanotubes into cells. So we've done some work on this. And the main objective of this is to use the carbon nanotubes for their optical and thermal properties. So we can design the peptide to get the carbon nanotubes to interact principally with tumor cells using folic acids. And once you get them into the tumor cell, if we all know, all the biologists in the audience know that the optical properties of skin is very interesting in that in a region from around 600 nanometers to 1400 nanometers, it's almost completely transparent. Okay? So in that particular region, the carbon nanotubes have a very high absorption of light. So once we internalize the carbon nanotubes into the tumor cells, and we excite the cells with a laser in that particular region of the spectrum, that the skin is transparent, but the carbon nanotubes are highly absorbing, then the photon of light gets absorbed, creates heat, and kills the tumor cell. Okay? So this is begins to allow one to think about localized therapy in the body by utilizing these nanostructures. Okay, so how then do I take my nanostructured materials, form them into a macroscopic structure that is the strongest material ever found, or the most electrically conducting material ever found? Well, people have done a lot of work on incorporating carbon nanotubes, or graphene, or metal nanowires, clays, lots of different nanostructured materials into polymers or metals, and trying to make, a material that has higher mechanical properties. And this is a very good example of this. This is a baseball bat where they've incorporated a small amount of carbon nanotubes. So the baseball bat's price has gone from maybe $100 US to about $600 US. And the only difference is that it's got carbon nanotubes there. There's no mechanical performance. So the bat is the same with or without the carbon nanotubes, because they haven't managed to put them in a controlled fashion. But at least you can have a stealth bat when you go out and miss the ball. So what do we do to overcome this problem? Well, there are many ways to assemble the carbon nanotubes. So one is making forests where they all self-assemble off a substrate like that. We can make fibers like this. We can make composites where we integrate them. Or we can make these kind of mass structures. But the key is to integrate them in a controlled way, as nature does. And if we can do that, and we can control the interface between our filler nanostructure and the matrix, the polymer, where we then begin to tune the interaction at that interface, we can then begin to utilize these nanotubes or other nanostructures for macroscopic systems. All right. So One of the things we'd love to do in terms of mechanical properties is to mimic spider silk. So spider silk is, in terms of mechanical properties, is an extraordinarily interesting material. So again, I guess nanotechnology has been around since Feynman 50 years ago or 60 years ago invented the term, right? So we've only really been doing it for maybe five decades. Nature has had 400 million years to do this, so we're way behind, right? So we can't possibly think about having the same skill set that nature has, but we can try and mimic it. So what amazes me about spider silk is it's got, on the nanoscale, it's got an extraordinarily complicated chemical and physical structure, but it's there for one thing. It's to catch missiles, right? So it catches flies, right? But so in order to do that, it has extraordinarily large toughness or energy absorption. And energy absorption is defined, if we look at the stress versus strain, okay, for a typical fiber. So for a polymeric fiber, it typically will go like that, and this will be about 100 megapascals. But for spider silk, it couples a part of the system which is very stiff, with then strain hardens and then elongates. Okay, so what this means is before the spider silk, the individual silk fiber breaks, all of this area under here is the work done as you stretch the fiber, and therefore its toughness or energy per unit weight. And so the bigger this area is, the bigger the toughness and the more energy is absorbed. And spider silk, for natural systems, far outperforms any other system. Okay, so could we do this with carbon nanotubes? Well, there are several ways to try and form fibrous systems. So one is based on what we call dry spinning. So we take a forest, so an aligned assembly of carbon nanotubes, and we essentially pull on one of them, and we begin to spin a yarn from it in the same way one would make a cotton yarn. Okay, and you can form different structures. So this is a single ply yarn. You can do double ply. You can do more complicated structures. And this is just a scanning electron micrograph image of the individual yarns that are being pulled from the forest. Okay, so you can see here there's maybe 100, 200 different individual fibers that are forming this yarn here. Another way we can do it is through what's called coagulation, and we can begin to mimic spider silk structure using this particular method. So we take a dispersion of the carbon nanotubes, and we inject it into a flow of polymer, and that all aggregates together, and you form a gel which you can then dry into the fiber. I've just realized this does not have to be a wooden table. It can be anything. I need to get my student to change that. And so what does that mean? Well, if we look, so this is, we're injecting our carbon nanotube ink into a co-flow of the polymer, and it immediately forms a gel, right? So you can see that there's some instabilities here, but this gel contains around 68% carbon nanotubes. And you can collect it and dry it, and you end up with a dry fiber. And this is the resulting cross-sectional structure. So you've got these carbon nanotubes that are integrated into the fiber in a very controlled fashion. And if we look at the mechanical properties, so this is if we plot this strength versus strain. So I said to you that for a tough material, you have large strength and large strain at break, right? So you're somewhere up here for toughness. So to give you an idea, this is a universe of materials. So up here we have ceramics. So ceramics are very brittle, so they don't have much strain before they break, but the strength is very large. Like so-called superfiber materials like Kevlar is up here, okay? But our nanotube fibers, depending on the morphology, has very impressive properties. So it has very large toughness, but it also has strength at break, which is close to 3 gigapascals, okay? So, and the reason for that is, I won't go into it today, but the reason for it is that the dynamics of the carbon nanotube and polymer interaction at the nanoscale is very similar to protein-protein interactions in spider silk. So it's really it's kind of utilizing the building assemblies of nature, but using wholly synthetic systems to do it. And this is just a quick, I don't want to go into this too much, but if we look at the energy absorption and compare it to spider silk, so one can see for stress, the strength, the amount of force applied before the fiber breaks. For nanotubes, it's close to 4 gigapascal. For spider silk, it's 1.8. But the really impressive number is if we look at this toughness or energy absorption, so spider silk, which was the toughest material in nature, has 150 joules per gram, which is a lot before it breaks. But these carbon nanotube fibers are 600 joules per gram, so a factor of 4 better than spider silk. And there's other things we can do because, okay, we can use them for their mechanical properties, but because they're electrically conducting and they're thermally conducting, and they also have very high surface area, so you can use them in batteries and capacitors, there's a range of applications. And this is just a few. So one, you can make electronic textiles, right? So these are highly conducting. This one here is one of the first ones we made. It's very naive, but it's actually supercapacitors formed from the fibers wrapped around into a wire supercapacitor. And they perform in a comparable fashion to commercial supercapacitors. Another interesting fact is that if you inject charge into these carbon nanotubes, the bonds have to change their length in order to allow for the increased electron density. And one can use this to make actuators or materials that change their dimensions once you inject the charge. And we make electromechanical actuators out of this, or so-called artificial muscles. And the first generation one can produce with carbon nanotube fibers is an order of magnitude better than natural muscle, because the building blocks are so much stronger than the building blocks used in nature. Okay, so what I'd like to show you now is, so in nature there's beautiful constructs based on templated assembly. So if you look at honeycombs or the cross-section of a tree, so you've got an assembly, a corrugated assembly of scaffolding with pore structures in it to get water up and down and so on. And if we could try and mimic that in synthetic systems, we could begin to produce very low-density materials that have very high strength or very high electrical properties, and really begin to produce materials that nature just can't produce, because we're using building blocks that they can't, or nature doesn't have its hands on. Okay, so how do we go about doing this? Well, one can use polymer templates to force our nanostructures to take on particular nanoscopic and macroscopic assemblies. And we do this by using latex beads. So latex is essentially, it's aqueous paint. So it's nanospheres of polymer, typically between 50 nanometers and 300 nanometers in diameter. And on the surface, they have a coating that makes them water soluble. And when you put them into water, you've got a stable suspension, so these polymer particles in the water. So aqueous-based paint is based on this type of structure. And this is what the paint looks like. When it dries, and if it's soft enough, it forms a clear coating. This thing here, the movie stopped, but this thing here is a pressure-sensitive adhesive, so Post-it stamps. They're based on this type of material. But the idea here is we take these latex spheres, and when they form a film, they form this beautifully ordered structure. So this is 4 by 4 microns, so these are 200 nanometer particles. And you can see they form this beautifully hexagonal close-packed structure. Okay? And if we take a Fourier transform of that, we can see the ordering in the image. So what happens when we add carbon nanotubes? Well, we add them in the dispersion. When the system dries, the idea is that the polymer particles come together, and they force the nanotubes to assemble at the interstitial points. So depending on how soft or hard the polymer is, if the polymer is hard, so it doesn't form a film, you end up hopefully with a segregated structure, like a honeycomb, a bee honeycomb. If it's very soft, then the carbon nanotubes or the other nanoparticles can diffuse into the polymer structure, and you end up with some kind of random network. And I won't go into the physics, but you can understand this in terms of the capillary forces during drying. So if it's a very soft system, this is an atomic force micrograph image. So you can see that the carbon nanotubes are isotropic, randomly arranged within the matrix. So not too interesting. But if we go to this situation, where the so-called glass transition temperature, so how hard the polymer is depends on its temperature, and this particular polymer will go from soft to hard around room temperature. Okay? So we get this amazingly beautiful self-assembly of the carbon nanotubes. So this is an SEM image. So roughly, I don't know what that is, maybe 15 microns across. And what's happening is the polymer particles are coming together, and they're forcing the carbon nanotubes to assemble into these hexagonal arrays. right? And this is truly large-scale self-assembly. So we're showing this happens on centimeter, bigger scales, right? So it's because we're playing off the temperature in an aqueous environment in a very similar fashion to natural self-assembly. The nice thing about this is that you can utilize that the matrix, the polymer, we can stretch it. If we stretch it, you end up with the carbon nanotubes being elongated too. So you get this this nice elastic system where the nanotubes can elongate, but they remain in this ordered system. What's very interesting here is that these particular systems allow us to make stretchable conductors. So why is that interesting? Well, if you take a normal composite system where you add an electrical filler and you pull on it, the nanoparticles will move and they'll break their connection to each other, and you lose your electrical conductivity. In this particular case, the carbon nanotubes are in these interstitial sites, but they're just sliding along each other. So they maintain electrical contact throughout. And so you can stretch this to 300% of its original length, and the conductivity only changes by 1%. Okay, so a small amount of physics, but it's important because it goes into really cool stuff in a second. I think cool anyway. So if you take a bunch of rods and you throw them into a box, and say the box is filled with water so they can float around or whatever, and you keep adding the volume fraction of those rods, eventually they'll contact each other, and you'll form a so-called percolating network. Okay? And if those rods are electrically conducting, well then you turn on electrical conduction. And that's at a particular volume percent. And the amount you need is dependent on the length of the rods and also the diameter of the rods and how stiff they are. And so if we were to plot for a particular box of rods, we have conductivity on the y-axis and we have the fraction of rods we're putting in there as a function of volume. So in region 1, where the rods are very low density, they're not contacting each other, so we get no electrical conductivity. And then suddenly, at some particular point, which we call the percolation threshold, they begin to contact each other, and the electrical conductivity shoots up. Okay? And then you begin to add more, and then it's a small amount. So as you make more connections, the conductivity goes up a little further. But the interesting thing is this percolation threshold, which is this thing here, is inversely proportional to the excluded volume. Right? So if I take my box and I begin to take regions of the box and put other stuff there where the carbon nanotubes can't go, well, I'm increasing or modifying the excluded volume. So how do we do that? Well, we can use our latex particles to do that. So think about, we take a box and we add all our spheres, right? So the spheres will order into some kind of closed pack regime, and the only volume allowed for the carbon nanotubes to go to is the spaces in between the balls, right? So everybody who's done undergraduate physics will know, okay, so if I take a hexagonal closed pack arrangement of balls or atoms, what's the free volume? What's the fraction of free volume? First year solid state physics. Depending on whether it's FCC packing, so face-centered cubic packing, or hexagonal closed packing, it's roughly around 24% or so. Okay? So there's now, instead of having 100% to fill space, we've got roughly a quarter of that. Okay? So if that's the case, then the percolation threshold should become very, very small because we're modifying the excluded volume. And that's the case. So if we look at the conductivity versus carbon nanotube concentration, okay, so for the isotropic system where the carbon nanotubes can kind of go everywhere, we see this behavior where this percolation threshold happens at around 0.4%. In the segregated network, where we're now forcing the nanotubes to go to smaller volume, or there's lower fractional volume for them to exist in, we now have this percolation threshold down at 0.1% or so, which of course is 25% of the original one. So it works. Okay, so a question. I'm probably forcing most of you to fall asleep now, so we'll try and keep it interesting. So this is a history lesson as well as a question. So what is the relationship between Greek philosophy, the Olympics, and this is a very apt point, Brazil with the Olympics, James Bond, to keep the theme going, and electrical percolation. Now, before we go on, it's a very tenuous link. Very tenuous. But we'll continue. Okay, so no one's going to get it, so I'll just go. Right. Okay, so the Olympics and Greece. Apollonius of Perga, around 200 BC. He was one of the first mathematicians, and he was really interested in looking at how spheres fill two-dimensional space. So we take a big sphere, three-dimensional space, sorry. So you take a big sphere, and you put lots of small spheres in, and you try and optimize the packing. Okay? And then this guy came along, which is an American engineer called Clifford Furness, and he was a geologist, and he was interested in looking at how water diffuses through clay. For he's a mineral engineer, mining engineer. And so he developed the ideas of Apollonius and wrote down some mathematical expressions to look at how particles pack. Okay? And he also represented America at the Olympics he represented the 800 and 400 meters, right? So there's a link, I'm not lying to you. Olympics, packing of spheres, and Apollonius of Perga. Okay, so these guys then worked on this, and of course now he went all the way back and the Greek thing. So okay, so how do I incorporate James Bond into this discussion? Well, I choose Pierce Brosnan because I'm Irish, and he was Irish. So we'll use him for the rest of the discussion. Our friendship is finished. Okay, so how do I relate this to electrical percolation? So this is my little electron James Bond, and you can tell he's a James Bond because he's a little dicky bow in him. And he wants to get to the bad guy, Blofeld's over here, right? So Blofeld's sitting there rubbing his cat. Now, if James Bond is in a non-segregated system, he goes all over the place, and it takes him too much time to get over here, and the baddie gets away, right? If we have a monodispersed colloidal system, so these are the bad guys. This is Jaws, and I can't remember the little guy's name. What's his name? That's the one. So James Bond has to avoid these guys, so he kind of moves around them, but it still takes too much time, and the baddie gets away. Now, if you put smaller balls, and these are the Bond girls, right? So you've got the Bond girls in between the baddies, and this is laid on in the movie, so he avoids the Bond girls. Early on, he attracts to them. But in this situation, he needs to avoid them to get at the bad guy. And there's less path for him to take, so therefore he makes it in time and he catches the bad guy. So how do we relate that to electrical percolation? Well, we have our original big ball structure, and now we put small balls in between. Okay? So the fractional volume available is much less, and therefore the percolation threshold is even lower. So I think that's pretty good, right? Tenuous at best, but there's a good relationship there. How many people can say you can relate electrical percolation to James Bond? It's all the beer you've been feeding me. All right, and this works very beautifully. So if we look at the AFM images, so these images of the nanoscale building blocks, these are the big polymer spheres surrounded by the small polymer spheres, and then the carbon nanotubes go in, and you can see that they actually have to wrap around these small spaces. And it turns out then that the percolation threshold maps beautifully with the change in void fraction as you add the small spheres. So here we have a 270 nanometer sphere, the big ones, 50 nanometer for the small ones. The void fraction goes like that as you change the volume of the small spheres present. And if we plot the percolation threshold, it reduces as well until we get down to 0.002 weight percent. Okay, so we started with 4 weight percent in an isotropic system, went down to 0.4, then to 0.1, and now we're at 0.0028%. So it's practically transparent, yet the electrical conductivity is the same. Okay, how am I doing for time? 2 hours. Fantastic. Okay, so there are other application areas in this for these particular systems. And one is trying to manipulate the expansion and the thermal properties of the composite systems. So this is our latex and our carbon nanotubes surrounding the latex spheres. If we heat the system, what happens? Well, the coefficient of thermal expansion of the polymer is a lot bigger than that of the carbon nanotubes. The carbon nanotubes are very rigid, right? So you need to put a lot of energy for the bonds to expand. So essentially we have a thermal sensor based on the expansion. So this is our colloidal particles, this is our nanotube belts, and as we increase the temperature, the polymer wants to expand in all directions, so X, Y, and Z. But because the nanotubes are there, it can only expand in the Z direction. So you get all the volume expansion in a linear direction. Okay? So it's a bit like Homer Simpson drinking too much beer, the beer belly, and a belt. So he tightens his belt. The belly has nothing to do but to go whoop, and then out. Right? So this is, unfortunately, I'm resembling Homer Simpson a little too much, but and it works out really beautifully. So if we look at the volume expansion, so we measure the change in thickness as a function of the temperature, and we do that for different CNT weight fractions, we can see that the overall change in the Z direction is 3 times what one would expect for the volume. Right? So it works really beautifully, and it behaves as a very quick thermal expansion system or thermal sensor. Okay, so just to say a little bit about some other nanostructure materials. So we also work a lot on graphene. Graphene is a very exciting material for its physical properties because it has very interesting electrical properties. But like carbon nanotubes, it's extraordinarily difficult to process. It comes in graphite. You've got to tear each individual sheet from the graphite and then try and reassemble it into devices. Okay. But one can do that. So we can take a solution processable form of the graphene. So this is a very nice image. This is an individual graphene sheet. It's roughly 200 nanometers across, but it's 1 atom thick. Okay? So it's the fundamental synthetic building block. And if we can process it properly, we can get lots of these individual tubes. And this is just a range of different techniques to show that it's individual. But we now need to work out a way of processing this and assembling them into a material structure. And we do that using our latex assembly. So these are our polymer particles. When we add the graphene goes to the interstitial points. And at the edges, they overlap. And you get this like flower petal structure. But it's truly three-dimensional. So this image here is a Raman map. So Raman is a technique one can use to map out the chemical signature of a material as a function of X and Y. So the red bits are where the polymer are, and the green bits are where the graphene is. And this is from just different spectra. So we can map out where they are. So we get beautiful self-assembly or template assembly of the particles. So why is this interesting? Well, this again is very tenuous. But in the Harry Potter movies, so we had this thing called the invisibility cloak, right? So this is the cloak, he puts it on, he goes missing. And it's magic, of course. But there are new materials based on very structured or ordered materials where one can begin to manipulate light using the ordering of the material. And these are called photonic bandgap materials or metamaterials, is another way of doing it. And essentially one can see them as being the optical analog of electrical semiconductors, right? So semiconductors, for particular energies, the electrons will stay in one state until they reach a particular energy and they jump up into the excited state. Typical semiconductor behavior. In a similar fashion, if we're allowing only specific optical modes for photons interacting material to happen, well then we can force the photons to just take specific paths through the material. And perhaps we could actually, for particular wavelengths, we could get the material to reject the light completely and perhaps go towards this type of system. And this has been around for many, many years. In nature, it's been around for many million years. So these beautiful synthetic or natural structures, opal stones, they get their opalescent color from the fact that the silica spheres that form the opals are very ordered on the nanoscale. And when you have water in there, there's a change in the refractive index, and therefore you get this optical stop band happening, and you get these gorgeous colors. And in nature, many animals use it for attracting mates or for camouflaging themselves when there are predators around. So the butterfly is another very beautiful example. And one can, if for these graphene and carbon nanotube assemblies, if we spend a lot of time on the ordering and get very periodic ordering of the latex spheres, and then we incorporate the graphene or the carbon nanotubes in the interstitial sites, you begin to get this control of color. And this control of color is a combination of the change of refractive index between the balls and the filler, but also because of the enhanced scattering of the nanoparticles there. So this is a pristine material. Depending on the angle you look at it, it goes from green to blue, and it comes about from this beautiful ordering. For the nanosheaf sample, this is quite a nice, this is a, okay, why isn't the movie working? There we go. Oh. No. It definitely moved a second ago, didn't it? There we go. Okay, so if you look at it, as the angle changes, it goes from red to green. Okay? And this is coming about from the beautiful ordering on the nanoscale. And we can begin to tune that by changing the size of the spheres, by changing the type of nanofiller we put in, not just graphene or carbon nanotubes, but something else. So manipulating the change in refractive index. And therefore, you can begin to tune this stop band from the visible right out into near infrared. So it's not quite Harry Potter's invisible cloak, but it's getting close to it. Okay, so I'm nearly finished. I'd just like to mention one or two other things. So I hope I've shown you that if we try and control the assembly of nanoparticles, we can begin to produce really exciting or interesting macroscopic materials. But the real interesting physics and applied physics, I think, is coming about from hybridizing different types of nanoparticles. Okay, so making functional devices by coupling different types of materials at the nanoscale. And one of our major projects in my group is finding replacements for indium tin oxide. So ITO is used in all touchscreen devices. So the iPad or whatever uses ITO as the capacitive touch sensor. And indium is running out. And within 40 years, we're going to have to find a replacement material. And it's very difficult. Indium and, well, there are a few other oxide materials that have the similar properties, but indium is one of the only materials that is electrically conducting and transparent in the visible. Okay? So we have to find some kind of replacement, and I'm not going to talk about it too much, but this is one particular replacement. So we use silver nanowires as a film, and if you spray down a very low density film of silver nanowires, they're electrically conducting, but they are highly transparent because it's not a bulk material, right? So most of the area it takes up is free space. Now, the problem is that the junctions between the silver nanowires for electrons to hop from one wire to another, that energy difference or the change in work function is very large, right? So it limits the overall electrical conductivity that one can achieve. So what we've been doing is we've been putting so-called graphene blankets down at these interfaces. This is, the red stuff is silver nanowires, and the green stuff is this graphene stuff that we spray down, and it attaches itself, because of the surface energies are quite similar, it attaches itself at junctions, and basically reduces the contact resistance. So with these types of materials, you have a very cheap, a very flexible material that has better properties than ITO. Okay, so I'm not sure whether this is the future of touchscreen displays, but it's definitely a first step on the journey to producing materials that we can use as replacements for ITO. And so Antonio won't have to throw away his iPad. Okay, so I'll stop there. So I didn't do any of this work. I just sat in my office and waited for the results to come in, and then I get all the kudos. And so, but the real people who did the work on this particular stuff, on all the latex stuff, is Isabella Jurlovic. She's a postdoc in my group. Pat Warajitafan, he's just finished, and Alice King. But all of these people contributed to some extent. Acknowledgements. So these are the funding agencies that make the work happen. And I've also my collaborators at Surrey, at Trinity College in Dublin, and University of Texas. And I'd like to thank you very much for listening to me.
Okay, thank you, Alan, for such an exciting talk. I mean, it was pretty good. I'm really happy. I'm your friend because I believe you're going to be rich soon. So
don't hold your breath.
No, I mean, So we have time for questions. Whoever has questions, we are open for questions right now. So feel free to ask. So, this was a very nice also. Is this working? Yes. So you can ask even basics, questions. Questions?
The basic questions are the hardest ones.
Yes, I have to. I agree. Totally agree. Totally agree. I mean, I have one question to start with.
Yeah.
So in the material you prepared for when you make the correlation between the James Bond and the electric conductivity, so what is the advantage of having just like smaller in volume paths for electric current? I mean, it won't be better just to have a whole bunch of Carbono nanotubes and conducting much more charge?
Yes. The main reason we do that is for this transparent electrode application. So you need to optimize the transparency, so approach 95% transparency in the visible, but maintain the electrical conductivity. And therefore, by pushing the percolation threshold to the lower level, you need less material, and therefore the transparency is high. So that's the only advantage of this particular. But you're right. If you wanted to optimize the electrical conductivity, we just throw as much in as possible.
Right. Actually, maybe related physics question.
Oh, good.
I was looking at my son, was having these questions in his physics. So let's say if you have a square grid of wires with certain resistivity, let's say a carbon nanotube, I try to calculate effective resistance from one side to another. How that is compared if you say you have random structure?
Yeah, right. That's a good question.
My son knows how to do that for
that's a good question.
But grid, let's say.
So I mean, the physics is well known. So basically, lattice. So this idea of having it on a grid is the same idea as a segregated network. So lattice-based percolation is well known for 50 years, 60 years. So so it would reduce the percolation a lot. How would it reduce? So instead of having, that's BCC orientation instead of FCC, if you think about it, right? So that's higher excluded volume, so the percolation should be somewhere in between, I think.
More questions?
So my question is about chemistry. Did you talk about graphene from graphite?
Yeah.
So how do you obtain graphene?
How do we
you obtain?
It?
Yeah.
Okay. So we work with a group in Trinity College in Dublin where they use intercalation of solvent, and they choose a solvent that exactly matches the energy density of the surface of the graphene. Okay, so it's Onsager theory. We use, maybe you know Onsager theory. So we use the cohesive energy density of the solvent exactly matches the surface energy of the graphene. So in fact, there are maybe 10 to 15 different solvents that work very well. So the one that we use is NMP. Okay, it works really, really well. But it only works with a small group of solvents. It's very similar to how people exfoliated clays in the 80s and 70s. I mean, in my opinion, this method, I think, is the only method at the moment to upscale the production of graphene, because many people are working on CVD ground graphene, which is great. You get very beautiful, clean sp2 bonded, no dislocations. But the problem is it's grown on metal, and you have to get rid of the metal, put it onto a different substrate, and then try and do something with it. It's very expensive, and unless someone develops a way to do this on a 20 meters by 20 meters, this is graphite free, right? I mean, so if we can optimize this particular process, it's going to be. It could revolutionize mechanical composites, at least, if not everything else.
More questions? I have just a curiosity for the materials that have some potential applications in biology or in medicine. are they always their biocompatibility?
Yeah.
I mean, do you have a lot of metals in there and a lot of...
Yeah, I mean, so that's a good question. So the carbon nanotubes themselves, so this has been a very widely talked about problem or issue. The problem is with most carbon nanotubes, at least, they're grown from a catalytic particle. And typically we use iron as the catalyst, and iron is not very good for the body once it gets in, right? So the carbon nanotubes themselves, I think, are okay. The problem is that this catalyst particle is there. So in terms of this photothermal application, it's probably better to use metallic nanospheres, which have the same kind of optical properties in the near infrared.
You can also use like proteins or more, let's say, body-friendly detergents to improve biocompatibility.
So these particular peptides we've been using are synthetic peptides, so de novo peptides. They work very well, right? And they're biocompatible. But a lot of work has been done on using a range of different protein structures. I mean, I'm interested. That's one of the things I'd like us to talk about. But yeah, I mean, there's been a lot of work on different protein structures. Anything that's got an amphiphilic character will absorb onto a nanotube and make it soluble.
More questions?
Yep. You showed organized graphene and nanotubes that have optical properties. Mm-hmm. So, did you try to apply some potential, electrical potential, and it changed the?
That's a good question. Right. So, we're doing it at the moment. So a very interesting idea about this is that so graphene and carbon nanotubes are almost the ultimate black bodies. Okay. So if you think about a traditional light bulb, you take a piece of metal, you put a large current through it, and through resistive heating, we get emission. Now, if you were to try and think about the carbon nanotubes or the graphene as being a black body, which of course you put a lot of current through, will produce heat, which will eventually emit light in the black body spectrum. But now, you've only got this particular window that the photons can be released at. So instead of having this big, large emission, we can begin to tune the emission into very small windows. And all the energy has to go into that window. So you could have a tunable light bulb. I'm not sure why, but you can have a tunable light bulb nonetheless. What we are, I think it works. It's a good question.
More questions? I mean, if you, especially the students, I really like to, I truly believe that you guys have to take advantage of these people over here, the visitors, and interact with them. So if you want to ask questions, even in Portuguese, we will translate the question. There's no problem at all. So don't be shy. No? That's why I'm like holding my breath too for questions. So we use both. So for the electrical properties, we use single wall carbon nanotubes, but it doesn't really matter. Yeah, it's we buy them from several different companies. So there's a company in Belgium called Nanosil, Unidyme in the States. The cost of nanotubes has gone down markedly over the last 10 years, so it's not too bad now. Do they make pores in cell membranes?
There have been studies on that, and yes, I think is the answer, but it's not something I know too much about. But there's a paper in Nature Materials a year ago or so about that. So yes is the answer.
So they could act as those antimicrobial peptides and just like kill.
Ah, yeah. Yeah.
Could be.
Yeah.
See? More questions? No.
Oh, thank you for your presentation. It was really interesting. You're always talking about highly ordered self-assembly structures. Have you ever wondered working with metal organic frameworks?
Yeah, right. That's a good question too. So MOF materials, so metal organic framework materials, are really interesting. And I have a project with a colleague at Surrey he produces these MOF systems, and we're trying to integrate them into carbon nanotube scaffolds for sensors. Because they, in terms of surface area, I'm talking about large surface areas, so 1,500 meters squared per gram. But with MOF structures, you can go to 3,500, 4,000. So they're very interesting. I mean, they're not conducting. That's the issue. But if you can hybridize them with carbon nanosheaves or other electric or conducting polymer substrate, then I think there's a lot of options.
The ones I produce are conducting.
Oh, give them to me.
I'm going to start in September.
You are? Cool.
Yeah. The ones I'm producing are hexagons. There's a wide range of structures and organizations, and they are photoconductive.
Oh, wow.
It's pretty interesting.
Are you working with Oscar?
No,
Oscar
I'm working with
Yazidin?
Ravi at the ATI.
At the ATI?
Yeah.
Who?
Ravi Silva.
Oh, Ravi. All right. Yeah, good.
Okay. Any other questions? I'll give you a few seconds to think about it. Yeah? I mean, good. Pode. Claro.
Recentemente, uma empresa holandesa fez uma proposta de fazer uma colônia em Marte. Uma das promessas do nanocarbono é fazer um elevador espacial baseado em fibra de carbono de material básico. Eu quero saber o quanto longe a gente está disso.
Okay. So this is a very tricky question. Okay. Please correct me if I translate it wrong. Okay, that's right. So he's asking that he recently heard that there is a Dutch company that wants to colonize Mars.
Yeah, I heard.
And they said that there will be a kind of an elevator made out of carbon, to get there. So how far are we from that?
So it's very interesting. So when Richard Smalley, who won the Nobel Prize for C60, he was one of the first people to make carbon nanotubes. And Arthur C. Clarke, the author, contacted him and said, in one of my books many years ago, I talked about a space elevator in geosynchronous orbit. And I made it out of a material that I didn't know what it was. I just called it a carbon-type material. And he actually asked Smalley, could he change his book and put carbon nanotubes in as the material. So the new versions of, I think it's, I can't remember the name of the book, but it's a new version of the book has carbon nanotubes in it. But to answer, in reality, I wouldn't go up the elevator if there was one. Yeah. No, the problem is that you need a matrix to put the nanotubes into. And the temperature differentials and so on, I'd be more worried about the matrix failing than the tubes themselves. So if someone could produce, nanotubes of kilometer lengths with very small diameter, then it's maybe a reality, but not at the moment.
More questions? Is everybody? I mean, if you can also, ask questions later, there's no problem with that. Okay, so let's thank Alan again for such a nice talk. Thank you very much.